Rightio, so let's discuss our bicycle geometry and compare it to the question that we've got and compare it to our ANSYS geometry, and hopefully it'll all make sense. Right, so here, question. This is your question that you must solve. And this is a bicycle. Now you see the parallels, right? This is the crank, this is the crank, this is the rear sprocket, otherwise known as a cassette. That thing. You got a chain, you got a chain, you got a frame. Frame goes up to there. So our model only models like this bit, doesn't capture this front fork, which is a slight imperfection in our model, but at this point we're not up to learning the correct way of modeling that. I will teach you later if you want. So we don't have explicitly attachment points for the front wheel, but we can deal with that by just kind of superimposing it and pretending that there's not much moment going on here. What kind of distance is that? It's probably like 200 mil, maybe 150 mil. Shouldn't be catastrophic. Anyhow, let's think about the constraints that you need to apply in order to achieve a valid analysis. So these wheels, right? If you sit on a bike, you sit on it, and the bike is being held up by whatever, assume that you're extremely good at balancing. What kind of reaction are those wheels applying to your mass? Well, they can only apply a reaction in the vertical direction. They can only apply a reaction in the vertical direction. And more than that, the two dropouts, the 2 points at the rear of the bike, this one and this one, can rotate about this point, can rotate about the center point of that axle. What I mean by that is the bike can just fall over, right? Makes sense. Bikes have nothing explicitly holding them upright, which makes it extremely difficult to do our analysis properly, but that's okay. So, what we can do is we can apply a displacement reaction to 1, 2, 3 points. 1, 2, 3 points. Now that allows us to model our wheels with some degree of precision, but it's not enough to do our analysis, because in order to do your analysis properly, you need to have your model constrained in all rotations and displacements. Otherwise you will get pivot errors, which happens like 3 or 4 times every tube. Also, as a side note, pivot errors also come from, I'll just demonstrate right now. People getting pivot errors, they solve and it comes up with like a big orange alert here and it says pivot errors, you know, something's not constrained properly, go to node XYZ. In order to solve that, you make sure you're in here, in your modeler, the green thing. Make sure that all your parts are selected, right click on them and say form new part. And then they're all one part. Because if they're not all one part, they're just like multiple different beam line bodies just flying around in space, and it doesn't really work. Cool, fun side note. Right, so we're here, and we're talking about our constraints. Now, how else can we constrain it properly? Well, we need to achieve these constraints in all rotations and deflections. So think about a cyclist pedaling hard, and there is a substantial moment along the x-axis, because the pedals are having a large force applied on them, and they kind of, you know, have like a couple going on. And the rider's out of the saddle, for example, out of the seat. And so that moment needs to be reacted somewhere. That moment needs to be reacted at the handlebars. So what you can do is you can have an X moment reaction at this node on the handlebars. Does that make sense? I hope so. The challenge with this is that we're trying to achieve something that I took quite a long time to learn, and you have to learn reasonably quickly. So it's quite alright to make mistakes, and it's quite alright to not really understand what's going on right at the start. But the faster you can get on to kind of trying something and getting something to solve and seeing what the solution looks like, the better, right? So get in there and try something out. So let's have a look. We've got our displacement. I've got a fixed rotation there. I've already done it. And this is a particularly shoddy analysis. But let's have a look. So let's look at my analysis here. I think I have done like a really long video of me discussing the correct solutions. But let's just cut to the chase. Okay, so we know that we need to have constraints in all rotations and deflections. So we kind of need to superimpose. We need to impose some constraints that aren't really naturally in the system in order to get our solution to be valid. Fortunately, many of these are kind of just there because they need to be there, and they won't have that much of an impact on our analysis. So, for example, a displacement in the x direction shouldn't affect our analysis very much, because there's no big forces in the x direction, except I suppose for the acceleration, and perhaps from the mass being accelerated. So, but what we do is we fix it here in the x direction, or indeed at the handlebars, somewhere that it's going to interact with the front wheel. That way, any acceleration force that you're having from the rear wheel can be translated through the entire frame, and we can capture that quite nicely. Okay, z-wise displacements. Well, there's nothing in the z direction, so there shouldn't be any reason we can't just chuck it there, right? So think about these forces and how significant they are to our analysis, and whether or not you can just not put too much thought into that particular constraint, or whether or not you need to translate the stress through the entire frame. And if, for example, it's like the z displacement, where there are no forces in the z direction, there are no forces that way, right? It doesn't really matter. It doesn't really matter where you put it. It's fine. Okay, now z-wise rotations. Okay, z-wise rotations should not be a huge problem. Hopefully, they'll all be reacted by the two displacement reactions of the wheels. Right? At least that's the idea. So we can probably put our z-wise rotation there. Okay, cool. Currently, we have a system that is not constrained at all in y rotations. That's a problem, because it will just spin around on the y-axis. So we can probably put it there. What we're generating here is a point around which the rest of the frame can kind of flex. The selection of that point is kind of a challenging thing to do, so I'm going to just kind of give it to you and let you kind of solve things and see how it all works out. But you are expected to understand this process for your exam, for your quiz that is coming up in like a couple of weeks, or next week. Anyway, finally, we need to constrain our x rotations. Well, we said that was constrained up there. So now I've got x displacement, which I can do probably on this node as well, and it should be fine. So you can just about do a fixed support there, y displacement there, and it'll probably work fine. There's a whole lot of reading you can do on this. Bicycle frames are, in real life, kind of under-constrained, and the way that the force goes through them changes depending on the rider, and it's quite a difficult thing to model properly. We gave you this system on purpose to get you to think about how stresses go through systems like this. It's important to be able to understand the stresses that go through a system and be able to mimic it, right? So why did we have this? Oh, there's one more thing that I forgot. We need to be able to get this member into compression. How do we achieve that? Well, we probably need to have an x displacement there and a compression force in the negative x direction there, right? Because this member we know needs to be in compression, because that's what we determined from our analysis before. So hopefully that's enough explanation for you to get something solving in this tute. Good luck.